1.3 is polygons, transformations, and animation. We're looking at the way matrices can be used in animations and stuff. Many industries use computer graphics. The video gaming industry relies heavily on computer graphics. Items in a game, such as a car, person, etc., are designed using 2D and 3D polygons and shapes. These shapes can be represented by matrices, which can then be manipulated mathematically to move items around in a game. I think that's kind of cool. The matrix for a shape has a column consisting of each corner point. The matrix for a 3D shape looks like M. So this right here is one point of the polygon. Notice it goes down, X, Y, Z. So that would be the three-dimensional shape, or the three-dimensional, I guess that would just be a point. So here's a two-dimensional shape. Maybe it'd be a little bit easier to think about 2 dimensions rather than 3 dimensions. Label the vertices of the 2-dimensional polygon, then form a matrix to represent the polygon in 2 dimensions. Okay, so this point right here is 1, 1. This is 5, 1. This is, what's that, 8, 3. And 5, 5. And 1, 5. So all I'm going to do is look at each of the vertices and then form a matrix out of this. And it doesn't really matter which one you do first, second, third, that kind of thing, but I try to make it go in some sort of order. So I might start with this one, 1, 1. Notice I'm going down. There's 5, 1, 8, 3, 5, 5, 1, 5. And that's all there is to it. We took that 2-dimensional polygon, took the vertices, changed it into a matrix. Later, we're going to do something, do some math with that matrix. But that's it for now. Example 2 is going to be a little bit harder because it's a 3-dimensional shape. There's a lot more going on. If you look at it, I see 8 vertices. Okay, so 8 points, 8 columns in my matrix. So it's kind of hard to orient your brain here, a 3-dimensional shape written on 2-dimensional paper, but that's what we have to do here. So let's go with this point is 0, 0, 0. That's a 3-dimensional point. Now, it's worth pointing out, usually when you see 3 dimensions, the z-axis is the one that's pointing up. That takes a little bit of wrapping your brain around, because normally we like the y-axis to be up, but usually in 3 dimensions, it's going to look like this. This one's the x, this one over here is the y, typically. So that's important, because if you don't know which one's which, you don't know which one comes first. The x, the y, the z. So let's go to point B. Obviously, the x number is 5, because it's 5 on the x-axis. The y number, though, you got to look at it. It doesn't go anywhere on the y-axis, so that y number is 0, and it doesn't go up at all, so the z number is 0. You got to really try to use your imagination here. This point C is going to be the same level as B, so 5 on the x-axis, but it also goes out to 5 on the y-axis. This has some y depth. It goes out to 5 on the y-axis, but it doesn't go up at all. It's still on the bottom of the shape, so the z is still 0. This point D, it doesn't have an x distance, but it does have a y. It goes out to 5 on the y. It does not go up at all, so that's 0, 5, 0. Those are your first 4 points. That's the bottom of that shape. So now let's do the top of the shape. Again, it doesn't really matter what order you do the points in. Let's go right here. 0 on the x, 0 on the y, 5 on the z. This one, you pay attention to what it's even with. It's even with this point, and this point has an x coordinate of 5. It doesn't go anywhere on the y-axis because it's even with this one, right? But it's also at the top, so that's your z coordinate. Your z coordinate looks like 5. 5, 0, 5. This point G, 5 on the X, 5 on the Y, and 5 on the Z. And this last point here, 0 on the X, 5 on the Y, 5 on the Z. I think that's the hard part of this, is just being able to visualize the coordinates. The easy part is now we put that into a matrix. So the first point was this. Make sure you go down. 0, 0, 0. I'm going to try to go in some sort of order. 5, 0, 0. This one is 5, 5, 0. Am I going to run out of room? This one, 0, 5, 0. Question? No, not really. I try to kind of trace around the shape, but it doesn't really matter which one's which. Okay, then let's go up to here. 0, 0, 5, 5, 0, 5, 5, 5, 5, and 0, 5, 5. All right, so now our picture has just become pure numbers, and that's how they're going to manipulate it. We can extend this concept to higher than 3 dimensions if necessary, but that image is going to be really, really hard for us to visualize. Think about how hard it was to visualize 3 dimensions. 4 or 5 might be impossible for our brains to handle. A computer could do it, but it's going to be hard for us. Types of transformations, you might remember this from algebra class. A translation is sliding it in one of the 3 directions, X, Y, or Z. Scaling is going to make the thing bigger or smaller. Maybe you want Mario to grow to twice his size or something like that. So you're trying to grow or shrink something. Rotation, I'm going to spin it around one of the axes, X axis, Y axis, Z axis. Number 3, give the matrix for the figure shown below. Then draw the translated figure given by sliding right 3 and down 2. Okay? Right 3 and down 2. Give the matrix for the translated figure. So think about the points here. We've got 0, 2, 4, 2, and 2, 4. So the matrix would be 0, 2, 4, 2, 2, 4. And again, it doesn't matter which order you put the points, but that's that. So now I want to slide this thing. I'm going to slide it right 3 and down 2. So just take each point and go 1, 2, 3, 1, 2. Right 1, 2, 3 and down 2. It's going to be there. Right 1, 2, 3 and down 2. Notice it holds its shape. I just slid the thing right 3, down 2. It says give the matrix for the translated figure. So look at your new coordinates. 3, 0, 7, 0, 5, 2. Three, 0, 7, 0, 5, 2. You're supposed to notice something. Yes? Question?
When you translate it, do you have to put the coordinates in the same spots, like when you make them?
Yes, yes. Once you put those coordinates down in a spot, yes, you want to leave them in that same spot. So if we picked this one first, you want to make sure this one's first. Okay? This one it was here, so its corresponding point should be in the same position. Great question. You don't want to shuffle them in the middle of the problem. Okay? So good observation, good question. You're supposed to notice, basically you're supposed to notice how to get to here from here. From here to here. How could you get the final matrix without drawing the figure? Right. We're talking pure math. We don't really need the picture anymore because we can just look at the numbers. If we know we're sliding right, we're going to add 3 to the x, and we're going, what, down 2? So we subtract 2 from the y. And computers are going to be really good at doing this, right? We don't have to visualize anything. We can just tell it what math to do. Uh-oh, where's my slide? All right, here we go. Okay. Homogeneous or homogeneous coordinate transformation. It isn't that difficult to translate by adding, subtracting to each coordinate, but you'd have a different calculation for scaling and another different calculation for rotation. By using the concept of homogeneous coordinate transformation, all transformations can be done with a single matrix multiplication. Right? That's kind of huge, because we don't have to worry about adding or subtracting or whatever. Everything can be done with matrix multiplication. It takes a little setup, but isn't too hard after that. In general, you must add one dimension onto your matrix. A two-dimensional shape needs a third dimension in the matrix. A 3D shape needs a fourth, and so on and so on. To translate the figure, multiply the translation matrix by the matrix of vertices as shown. Okay, so one thing to notice, I made a mistake in my notes, and then I copied that mistake for subsequent problems. So I made kind of the same mistake several times, or a similar mistake anyway. So right here, this is supposed to be t sub y. Fix that. And this is supposed to be a 0. T sub y. Okay, so make those changes. I made a similar mistake right here. This number is supposed to be a 0. So let's go ahead and fix them all, I guess. If you look down here at the bottom, this number right here is supposed to be a 0. And this number right here is supposed to be a 0. So I kind of made the same mistake and then just copied it a bunch of times and pasted it when I made these. So sorry about that. Make sure you fix that. Otherwise, your numbers are all going to be wrong. Okay. So T for translation. Okay. Actually, I think that should say transformation. Transformation. Because, well, I guess here we're translating it, but later we might be rotating it or scaling it or something like that. Okay, so it's not technically wrong on this slide. T for translation, T for transformation, but this first matrix is how we tell it to move, how we tell it to change. And then the matrix of vertices, that's this, and you're going to add this row of ones at the bottom. So we see our XY point for a two-dimensional, or we see our XYZ point for a three-dimensional, and then we're going to add a row of ones on the bottom. Remember, up a little bit, it said add an extra dimension onto the matrix. That's what we're doing. Okay. TX. T sub x is the amount you move in the x direction. T sub y is the amount you move in the y direction, and T sub z is the amount you move in the z direction. That's these numbers right here. This is where you're telling it how to move. Right 3, down 2, and so on. So here in this slide, I just tried to summarize everything. So these are all the transformations we're going to use. And this is in 3 dimensions. We might do 3 dimensions, we might do 2 dimensions, but this is the same thing I just gave you, the translation. But this is what you would do if we scale it. So if you wanted to double it in size, putting a 2 right here would only double it in the x direction. you'd have to put 2 here, 2 here. You would double, double everything in the x direction, the y direction, and the z direction. All right, so whatever the number is, could be 0.5 to cut it in half, to shrink it. Rotation, notice it's going to take a little bit of trig, some sines and cosines for rotating it around the x-axis, y-axis, or z-axis. Those would be different calculations depending on which one. So we've got translation, we've got scaling, we've got rotations. This is kind of your reference. This is what you'll need to go back to probably later if you're trying to do one on your own. Note, you can multiply any number of individual points in the XYZ matrix. What that means is you don't necessarily have to multiply every point. Maybe you just want to move 1 point, okay? And if you wanted to just move 1 point, then you would multiply your translation matrix times that 1 point, okay? Because we know this is a 4 by 4, and if we multiply just this piece, that is a 4 by 1. We know we're allowed to do that. We know because these two numbers match, and we know that answer would be this. So we could just do one column of that if we want to, or any number of columns actually, without doing the whole thing. All right, so here's where you're going to need your calculator, I think. So get your calculators ready. Below is a 3D shape and its corresponding matrix of homogeneous coordinates. Find the matrix that corresponds to the shape after being rotated 60 degrees around the x-axis. 60 degrees around the x-axis. Okay, so what I would do is I would go to your reference on the previous page and find the one that's talking about rotating it around the x-axis. That's this one. So this is your T matrix that you're going to need. Okay, that's your basic form, but we're talking about 60 degrees, so we're going to need to put a 60 degrees in there. A lot of ones and zeros, so that's good, that's easy, but the cosine 60 and the sine 60, that's what's going to be kind of difficult. Okay, so one, zero, zero, zero. 0 cosine 60 degrees, negative sine 60 degrees, 0, 0, sine 60 degrees, cosine 60 degrees, 0, 0, 0, 0, 1. Try really hard to keep things lined up in columns. Okay. Anybody remember how to do cosine 60? Cosine 60 is 1/2. You might remember that from last year. We did that a lot last year. Cosine 60 is 1/2. Sine 60 is square root of 3 over 2. Okay, we've done those kind of problems. I mean, that's not the point of this problem at this point, but if you knew that cosine 60 was 1/2 and sine 60 was square root of 3 over 2, that'd be negative square root of 3 over 2. I suppose you could have written the matrix like that and taken the trig out of it. And in fact, I think my calculator that I'm about to use won't let me plug in the sine and cosine stuff. So I'm going to have to get out a calculator or something anyway. So let's say, what do we have? Cosine 60 and sine 60. We've got 0.5 and 0.866 will be my decimals that I'm about to use. So I'm going to type this in because, well, just because. So here's the website I like to use. Problem is I gotta make everything the right size. So matrix A is my matrix T, and that's got to be a 4 by 4. And then the next one is That's 5, 6, 7, 8. It's a 4 by 8, but the thing about this website is it doesn't let you, it only lets you expand this to a square. So I don't need all of these spaces. I'll just use what I need. So matrix A, 1, 0, 0, 0, 0, and then cosine 60 was 0.5, negative 0.866. Now I rounded off, so I'm going to be off just a little bit, but that'll be okay. And 0 and sine 60 was 0.866, cosine 60. Okay. If you have a graphing calculator, I think that will let you type in sine 60 and cosine 60. I think as long as you're in degrees, I think you'll be fine. All right. This website will not let me do that. So this one. Okay. So I can just leave all these other rows blank. I don't really need them. And I'm going to multiply this times this. So in this little box, I just go A times B. And that gets me what I need. Okay. That gets me what I need. So let's just, I'm gonna be lazy here and I'm gonna copy and paste that over. That would be your multiplied matrix. Okay. So then, you can copy those down. You can write those down. If you've got it on your screen, then great. If you're watching the video, maybe pause it because I don't want to spend all day on the video part. All right. If you don't have it copied down, we can come back to it a little bit later. The question says, what are the coordinates of point C prime, or in other words, the coordinates of C after the transformation? Okay. Well, which one was C? So let's look at this. Point A, and it's really hard to visualize this, but A is even with this 4, and then 0 on the Y, and then 1, 2, 3, 4. It's really hard to tell that that's 404. Okay, 404. But that's this. Okay. And B is farther out on the x-axis, so that must be 6. That must be 604. That's B. Point C is the one that we want. Notice it's even with this B. Okay. So that tells me that it goes out this far, 6. And it's way out here on the y-axis. So 1, 2, 3. It's actually really hard to tell, but it must be this one. This one must be the point C. 6, 4, 4. So when they ask me for point C prime, it must be this one. That must be the point C prime. Okay, back to our question from earlier, we know that C prime is in the same position as C. So what are the coordinates of point C prime? It would be 6, negative 1.464, 5.464. Now again, those numbers are rounded, but that's still a pretty good approximation of those numbers. Okay. Let's move on. This object doubles in size, then is moved +3 in the y direction and -5 in the z direction. What are the final coordinates of point B? Okay, so there's a lot going on here. First, we want to double it. Okay, double in size. So go back to your reference, and you're going to see that we're going to need to 2, 0, 0, 0, 0, 2, 0, 0, 0, 0, 2, 0, 0, 0, 0, 1. Go back to the reference. When we scale it, that was this one, okay? That's your important part of that scaling matrix, but that's how we're going to scale it. That's how we're going to double it up, double its size. Now, we have to double it first, and then we can worry about the translation, the sliding it, okay? But we need to do that multiplication first, okay? So I'm going to go back to my calculator, and I'm going to clean this one. And that was like that. Okay, so I still want A times B. I want to take this times this same matrix, I believe, right? And we get this, okay? So, so I know this is the first part of my answer, okay? No. All right, but now what I need to do is I need to translate it. I want to go 3 in the y direction and -5 in the z direction. So I'm going to need to do another multiplication. If you go back to your reference and find the one that's talking about sliding it, then that's the one that's going to look like that 0. That last 0 there is in the x direction. Nope. +3 in the y direction, -5 in the z direction. Wait. I messed that up, didn't I? Look like that. Okay. So I've got to multiply this times the answer that I just got. Okay. So, yes. Well, actually, yeah. Question was, if you can't hear that on the video, the question was, can't you just add 3 to the y and subtract 5 from the z? Absolutely. That's exactly what's going to happen. Okay. So if you realize that, that's exactly what's going to happen. So let's do that without even typing it in on the calculator, because it's going to be a pain. Okay. Good observation. So we're not changing the x at all, so we will end up with 8, 12, 12, 8, 8, 12, 12, 8. But we are going to add 3 onto every y coordinate. So just add 3 to all the y's. You're going to have 3, 3, 11, 11, 3, 3, 11, 11. We're going to subtract 5 from all of the z coordinates. 8 minus 5, 8 minus 5, 12 minus 5. And there we are. So if I wanted to know the final point of any of my, of any of the final locations of any of my points, I'm just looking at whatever this was. This would be a 2 prime, I guess, right? After 2 transformations. A single prime would be here, whoops, because this is A. So does it ask me a question about that? No. B2 prime, 12, 3, 3. Now, projection transformation. It is often necessary to view 3D objects in 2D space. Parallel projection, you might have used this. If you ever did like a drafting class or like an AutoCAD class, you had to take a three-dimensional object and try to draw it on a piece of paper with all the dimensions and stuff. That's this. That's parallel. That's parallel projection. Parallel projection is used in drafting because it's good for exact measurements. Parallel lines remain parallel, but angles are generally not preserved. This is good for drafting and engineering and stuff. Perspective projection is more like video games. It keeps a more realistic look. Close objects appear larger, but distance, angles, and parallel lines are generally not preserved. Okay, so there is a matrix for this. Parallel projection is pretty easy. It looks like, remember what the identity was? The identity would have a 1 here, okay? But all it does is takes that and gets rid of that 1. Remember what we're trying to do. We're trying to take three-dimensional objects and represent them in 2 dimensions, okay? And so it should make sense that all we can do, all we have to do is ignore the z coordinate. And so having this 0 right here knocks out the z coordinate, basically, okay? Perspective projection, like the video games, that's a little bit more complicated. But I guess the key here is this 1 over d, and it says d is the distance where the viewer is meant to be from where the viewer is meant to be on the screen. So like this distance right here from where the viewer is supposed to be and the screen, that's d. That's that distance. Okay, and we have a z in there somewhere. Z is the distance from where the viewer is meant to be and the object. So this is, well, this is another thing used in that calculation.